Thank you. So yes, next is John Scott, Principal Technologist for Power and Energy and Storage. He told me to say that he had 4 children, 3 of whom came all at once. And he also said that having 4 young children want things from him continuously and different things was not totally different to working with NASA centers. But he was prudent enough not to say which centers he was referring to.
Thank you, Ben. I'll add that when those triplets arrived, I was told that it would go by in a flash. It has. They're all graduating from high school next month and heading off to college. As Ben said, I have the honor to serve as the Principal Technologist for Power and Energy Storage for STMD. The power domain at STMD supports several of the strategic thrusts of NASA, but the main one, the one that requires most of our focus, is power for the lunar and Martian surface. Now, for the lunar surface, for lunar surface infrastructure, power is king, and given my role, I wouldn't think you'd be surprised that I would say that. But power is the key commodity needed to support, to exploit the lunar surface. And the scarce resource that must be harnessed and managed to produce that power is solar illumination. Now, illumination, of course, is available with rather long periods of darkness at the equator, predictably, but long periods of darkness. It is much more available over the course of a month at the pole, of course. But however, the illumination can be very intermittent. It's highly dependent upon elevation and location on the surface, on the pole. And for that reason, that's why that along with the fact its proximity to ice in the permanently shadowed regions, the Shackleton Crater has been selected, or is thought to be the main goal for the rim of the Shackleton Crater and its connecting ridge, are thought to be the likely place for the first NASA lunar outpost. In defining the gaps that must be closed in order to harness this illumination and provide a power system for a base at the lunar pole, we have the power team's defined a notional and prospective architecture. It's nothing, NASA's not defined as architecture, but it's something we're making an assumption about in order to define a set of building block capabilities that mission architects can assume will be available once they decide to design a surface architecture for real. Now, the scale and timing of these building blocks is being set by presumption about demand for power at the lunar pole. We think ultimately this demand will be driven not so much by the need for the foundation surface habitat or for a lab module, but by ISRU production of reactants and propellants from the lunar regolith. Now, the scale of that demand is a matter of projection, of course, but for the mature base, and again, Dr. Kleinheins will talk more about the ISRU development in the next talk, but the demand for this, we're thinking, will settle out at a mature lunar base at about 2 megawatts. From ISRU, the demand for power for human operations will be somewhat less than that. Now, our envision is that once the base or outpost at the lunar pole is settled and developed, there may be an expansion of infrastructure for human exploitation of the lunar surface beyond the pole toward the equator. This could cause power demand to grow single-digit megawatts at the pole, perhaps involving tens of kilometers of transmission distance, all the way up to gigawatt scale, perhaps, that of a small city with hundreds of kilometers of transmission distance. That growth will require some new building blocks, primarily among them the business of using ISRU processes to print cable conductors across the surface, and then have and also ultimately, if it becomes cost effective to do this, to use to gather lunar surface, lunar regolith silica to print photovoltaic arrays across the lunar surface. This could, of course, this is decades away, but it's something we have in mind for our advanced technology planning. Now, we have the gaps that need to be closed to create these building blocks split up between power generation, energy storage, and power distribution. The priority with which we need to pursue closures of these gaps is again set by the options that we have in mind for ISRU. ISRU is a killer app for power on the lunar surface. And we think it will be, there are two decision points really about ISRU, which will drive which type of power system we need to a large extent. So the higher priority in our gap closures is determined by which of these capabilities, which of these building blocks support more of the options available to ISRU. The first decision point for ISRU is, of course, is whether we're going to be making the propellant, gathering the propellant at the lunar pole from oxygen separated from regolith directly or from ice mined in the PSRs. That decision may take place in 2027, give and take a year. So, but the next decision point is to what extent we start expanding our infrastructure beyond the pole, which will involve power for ISRU construction materials, which is a much larger power demand, of course, than just the propellant mining. You can see from here that there's several of the capabilities, several of the gap closures that support all of those options, and some of the others just support really the business of operating in the PSR. So that's a rough priority the way we put on these gaps. Now, the first priority that we have is the development of a efficient surface power plant. This gap would be closed by coming up with a 40 kilowatt nominal power plant. There's a program underway now. There's a competition. There's a call out for design contracts that's open at the moment, collecting proposals. The purpose of this device is part to provide as a demonstration for a fission power plant that we might need for the Martian surface in the future, but it's also become a key part of the lunar surface architecture. If it will supplement any lack of illumination being able to be harnessed at the pole for the lunar outpost, and also it would be able to be, if it can be made relocatable, it could be used to power ISRU equipment to print conductors as we go toward the equator, and use it, and it can be used to, therefore, bootstrap a power grid that could expand across the lunar surface. A very important gap that we have to close here has to do with reliable Rad-Hard power electronics. The gap closure here is defined as having a suite of, bring to Tier L6, a suite of power management circuits that are 99% reliable for 10 years in the lunar radiation environment and can be maintainable in the lunar dust environment, meaning you can change out a circuit board in that dust. That involves a number of technological advances to be able to pull this off. The first thing I'll point out, though, is that it is the radiation hazard is the biggest problem here. Natural space radiation presents two types of hazards to electronics. One comes from the electrons and protons that are trapped in the Earth's magnetic field. We call that total ionizing dose. The other is from the heavy ions that are produced from solar storms and produced by galactic cosmic rays, from which the Earth's magnetic field protects electronics on the ground and in low Earth orbit, but to which they're exposed in geo orbit and on the moon. Now, the wide bandgap semiconductors that are ubiquitous both in aviation, aerospace, and in civil power utilities are inherently resistant to total ionizing dose effects, but the Achilles heel is the single event effects, latching, burnout, leakage current, that you can be caused by impact from these ions. Now, of course, there's high voltage switching applications for these semiconductors in the civil power industry, but they don't have to deal with the ions and hitting them on the ground. The geosynchronous satellites also have these semiconductors, and they're exposed to these single event upsets, single event effects, but they're only switching 30 volts usually. A failure or an impact of an ion when you're switching over 1,000 volts, which you might be for power transmission, can be catastrophic. So we don't know exactly how to solve that problem, except that it's going to be a combination of semiconductors, circuit topology, and shielding, optimized to maximize specific power, of course, across these circuits. Now, there are many options for people who are thinking about doing that. One thing that we need to, the power team thinks we need to be able to do rather quickly, is come up with a simulation method to predict the reliability of a given circuit design once it's proposed and considered for further advancement. Another high priority gap, of course, is transmission cables. There's really two parts of this gap closure. For the lunar pole, we're talking about cables that are Rad-Hard, lightweight, resistant to the environment, connectors that are dust tolerant as part of this gap closure. And we need to develop both AC and DC options. Which one we would have for a power grid is very much open and driven by the architecture itself. Mission architects will drive that, not our technology effort. It's an interesting problem for that. And it's driven very much by the length of transmission. 5 kilometers gives you maybe a DC system, 15 kilometers gives you an AC system. It's also driven by the power electronics at either end to both boost up voltage for transmission and buck it back down. One thing that we've noticed is that for a low frequency AC system, like for a civil power grid 60 hertz, there's heavy magnetics that come into play and make the either end of the system rather heavy. But those heavy magnetic circuits certainly are Rad-Hard. So the reliability of the system comes into the trade as well as the mass. So again, there's a lot of work to be done here. Next, of course, for harnessing this low horizon illumination is photovoltaic arrays. We need to expand the state-of-the-art of photovoltaic arrays beyond the state-of-the-art toward 200-volt systems, 200 watts a kilogram, and enable them to be deployed vertically to catch the sun low on the horizon. The VSAT project is an example of a project we have going on to take steps in that direction. And that'll take care of matters for the lunar pole. As we expand toward the equator, we have the idea of we need to develop technology in the longer term that can be used to gather lunar surface silica and print PV arrays across the surface. Next, energy storage, grid scale energy storage. Again, for the pole, we have a concept of a regenerative fuel cell. The biggest challenge in developing what we need for that is not so much the electrochemistry itself, but the life durability. We think we need, for that building block, we need a 50,000 hour life. That's quite a challenge. It becomes a materials challenge, both in the membranes and the other components of the fuel cell system. We could stand some very basic fundamental materials research to develop that capability, that durability for these fuel cells. For the longer term, global lunar power system, we think we might need to develop flow batteries, the reactants of which can be drawn from the lunar regolith by ISRU processes. It's interesting. This is a new old idea, by the way. Jules Verne's Nautilus submarine was powered by a sodium flow battery. This is same application. By the way, it was a sodium and hydrochloric acid, which if it had actually been built, it would have been quite spectacular to watch it operate. Now we get into dealing in the permanently shadowed regions, the PSRs. Here's where we need power beaming. For production scale ice mining, industrial scale ice mining, we're thinking we'll need a building block that can offer 10 kilowatts transmission over multiple kilometers from a power source up in the sun or on the crater rim down into the PSR itself with a reasonably high efficiency. And we're thinking this is going to be a laser transmission system. As opposed to microwave, that some of the other power beaming work going on, it would be considered for other applications. A precursor or smaller scale version of this in the hundreds of watts could be very useful for powering prospecting rovers down the PSRs that would come into play much earlier than maybe help make that decision about whether we're going ice mining or regolith oxygen production. Another option for powering the rover in the PSR is completion of a project that SMD has had in place for some time for a higher power plutonium-238 based power source, a higher powered RTG using Stirling engines for conversion. That could provide enough, that will never provide enough power for industrial scale ice mining in the PSR, but it would provide a very good power source for prospecting down the rover. So this is a trade between getting this done and getting at least a hundreds of watt scale power beaming system in place. Also for PSR operations, we're going to need low temperature secondary batteries. Secondary battery modules, 50 kilowatt hour scale, or about what we would need for, say, the LTV and the elements, the other rovers that we have in mind, crewed rovers we have in mind for the for the lunar surface. In the PSR, we need that scale of energy storage to operate a mining machine, is what we're thinking. But our goal is to have the same specific energy and discharge performance that we get at, say, room temperature or at 0 degrees C, but have it in the 70 Kelvin environment of the PSR. That's a trick. We really don't think that we'd be able to distract the electric car industry, people developing batteries for that, to produce battery cells that can operate that way. They haven't got time for our piddly little moonshot. They're getting a lot of investment from otherwise. But that problem will have to be solved by thermal management. You know, there's insulation tricks that can be done, and there's the idea of radioisotope heat sources that can be very small and maybe involving other than plutonium, but other more ubiquitous isotopes that could, a small amount of that can go a long way in keeping the battery warm. Finally, we have another priority gap to close, more for Mars than for the Moon, although it could come into play with the Moon, is oxygen methane primary fuel cells. These would be useful, I think optimal, for powering a lander that happens to have LOX methane propulsion and a rover that would be part of a LOX methane economy. We don't anticipate a LOX methane economy on the Moon, but we do for Mars. So this is the fuel cell you would need to produce power from those efforts. There's some work going on now. It's maybe not as high priority as some of the other things, but it's something we need to keep going from Mars forward. We've also got gaps in mind for supporting the Explore thrust. They really cover the same areas that we're covering for the Live thrust, just different requirements. And again, the radioisotope power source at 500 watts is among these gaps as well. So in conclusion, our immediate focus is advancing TRL for power system components that we'll need to exploit the lunar surface at the pole. Longer term investments would be for ISRU-based operations that could produce and able to bootstrap the power grid as it expands across the lunar pole. And of course, all of this is going to be part of the RFI that will come out in a few weeks and invite all of your comments. With that, thank you for your kind attention.